So for part two of our notes for 12.1 and 12.2, just a little more look mainly at the formula that we dealt with where we said AB plus BC equals AC. So for the one that you're seeing here, this is now in terms of what we call a position vector. Position vector simply originates at the origin. And so these are just easier numbers to work with because we're using 0, 0 as kind of the initial point right here. So if I wanted to see this is vector OA. So remember what we've done so far in the past is we would do A minus O in order to get OA, vector OA. And so you can see because it's from the origin that I'm just going to get those coordinates as the vector. So here's that look right here. So if I did just 3 minus 0 for the top number and then 4 minus 0 for the bottom number for the vertical component, I just end up with the coordinates. So this is the x coordinate, this is the y coordinate if we're dealing with a position vector. And looking at these notes, I'm going to kind of encourage you to ignore the tip minus tail concept that you're seeing right here because students get confused on the wording of that. It's better seen if you see it as the terminal side minus the initial. So that's the best way to see those. So another look for the formula that we dealt with in the first set of notes is this one right here where we said that this vector plus this vector is equal to this vector. So again, this is if you were to jump in a boat and head this direction right here, but the current was traveling this direction, then the path that you would actually take is from O to B. That's the resultant that you would be on. And so that fits into our AB plus BC equals AC formula, but just in terms of the O's that we're dealing with right here for this position vector concept. So again, the easiest way I've seen this in the past is if you recognize that where this vector ends, the next one begins, and then that one goes to here. And so if I combine those two, right, I cut out the middleman, I cut out what they have in common, and I'm left with OB as the result. And so that's where we can get OB. If I take the same formula and just rewrite it, right, if I wanted to get AB by itself, then I would subtract the OA over to the other side, and I would say OB minus OA is equal to AB. Sometimes this is the easier way to work with it. So the same thing with the terminal minus the initial. If I were to look at this as B minus A, then it's vector B minus vector A gives me AB. And so there's just a couple of different ways of looking at it. It just depends on what problem they give you for which format you want to see it in. But again, it's just the same idea as far as doing the terminal minus the initial B minus A. So in this one here, even if we're doing it with the three-dimensional vectors, it doesn't really matter. So notice this has the three-dimensional components to it, but it's still the same idea. If I want to find vector AB, then I do the terminal minus the initial. So I'm doing OB minus OA in order to get this. And so if I just throw in those numbers into that format, this is where we would end up. So remember, there's two different formats you can write this in. This is in column form. This is in just kind of the horizontal format where you got to put the I, J, and K into your answer to get that horizontal format. As far as determining whether things are collinear, well, they need to have a common point and they have to be going the same direction. So they have to be parallel and have a common point in order to be collinear. And so we're looking for that. And so if this was vector, these were the components for A, B, and C. So if I wanted to show that AB is parallel to BC, so first thing to note is they already have a common point, right? They both share point B within those. So that's part of the rule to show that they're collinear. The other part is to show that they are parallel. So remember, parallel vectors are simply scalar multiples of the other. One could be positive, one could be negative, but either way, they just have to be scalar multiples of each other. And so if I were to look at vector AB first, so remember that's like doing B minus A. And so if I throw in the numbers that I'm given up top, so again, this is vector A, this is vector B, and this is vector C. So if I throw in the numbers that I've been given, if I did b minus a, so b minus a gives me ab. And if I did on this one to get bc, if I did c minus b, so terminal minus initial, then I get this guy right here. So you got to notice the numbers. If this is 8, 4, and this is 4, 2, well, one is simply a scalar multiple of the other. If I take these numbers and double them, right, then I get vector BC. And so if one is a scalar multiple of the other, then I know they're parallel. So because they're parallel and because they have the common point of B, then I know that they are collinear to each other. So same thing right here in number 2, if we're going to show that these are collinear. Just got to prove that same concept. So if I want to show that A, B, and C are collinear to each other, then I have to show that AB and BC are parallel, and that would also show that they have B in common. And so it's kind of those two things put together that shows that they are collinear. So they have to have a common point and have to be parallel. So if you want to give this one a try, this is really the exact same idea as number 1 that we just showed. So give that one a try and prove that they are collinear. So looking at the last part here, this is a really common IB style of question that you're going to see right here. So this is one you want to pay close attention to. Sure to be tested on this. So given the parallelogram that you're seeing over here drawn on the left, they're going to throw in a couple ideas. If you were doing this on your own, whether it's homework or on a test, you would want to start noting some of this within the diagram. When they say AP is equal to 2PB, so if APB is equal to 2 of these, somehow you might want to note that within your diagram. Or you could say that this is half of this is another way to look at that. If CQ is equal to QB, so you might want to mark those with or congruent marks or something like that, just to help yourself remember that rule that's given to you right here. So little a, vector A, is from O to A. So I would put a little a right there. I'll put a little c right there for OC, because everything now has to be done in terms of vector A and vector C. So for example, on the first one, for AQ, so if I want to go from A to Q, well, how would I get there? If I want to go from here to here, then what path would I have to travel on? Well, we would go from AB to BQ to get there, to go from A to Q. So remember things like AB plus BQ is equal to AQ. And so I just now have to put that in terms of these guys for vector A and vector C. So one thing to keep in mind, so what is this from A to B? What is that in terms of vectors A and C? Well, remember, if this is vector C right here, then this is also vector C. And so I can put C's and A's all over the place here, wherever I want to see them. So in terms of what we're looking for on this one, so I'm going to have to travel. So keep in mind, this was also vector A from O to A. So this would also be vector A from C to B. Well, these guys were congruent. So this is half of A. This is also half of A. So if I'm going to go this direction, then now I'm traveling in the negative A direction. So the way I want to get from A to Q would be to go from vector C and then the negative half A right there. And so that's where you're seeing the C minus half of A to get from A to Q. Right here, if I want to go from C to A, and again, this really helps if you're doing this on your own, if you've already filled in the little c and the little a and those types of things. But if I wanted to get from C to A, so what path would I have to travel on? I would go from here to here, and that's going to create CA. And so if I'm looking in terms of what we already know, if vector C goes from O to C, well then negative C would go from C to O. And so I'm going to go along the path of negative C plus A is going to give me CA. And that's what you're seeing right here. So I got the negative C plus A is going to get me there. Or you can call it A minus C, same thing. in terms of what we've already done, that would just be the terminal minus the initial. So A minus C would be the same concept. Right here, if I want to go from O to P, so right here I'm going from O to P along those lines right there. So again, think of in terms of what we've already done. From here, if I want to go from O to P, I'm going to have to go OA plus AP to get there. And so in terms of the C's and A's that we already have, we already know this is A right here. So I'm going to travel vector A plus whatever this is in terms of C. So remember that from here to here is all of vector C. Since these have a 2-to-1 ratio, then this is 2/3 of C. This would be 1/3 of C, so that we keep that 2-to-1 ratio that we have right here. So if this is 2/3 of C, and again, all these are things I would have labeled on my diagram to begin with, and that makes filling these in really simple and really quick. So I would have labeled all the A's and C's right off the bat before I even started answering all these questions. But then I could easily see that this is vector A plus 2/3 of vector C is going to get me there. And then again on number 4, if I want to go from P to C, so now I want to go from here to here. And so how would we do that? We would travel PB to BC is going to get me PC. And so to do that in terms of what we already have, remember this is 1/3 of C. This is now negative A going that direction. And so I'm just going to add those two things together and say that it's 1/3 of C plus negative A is going to get me from P to C. And then we just fill those in real simple. And these are things that should have already been labeled on the diagram. So we've already seen that this is 1/3 of C. We know that from here to here is A. So if I'm going backwards, then it's negative A to go that direction. And so then we just fill those in as we see them. But this is one of those concepts you're sure to be tested on. And if you have a hard time filling those in terms of like A and C or whatever vectors they give you, come see me for help. But these are ones that you definitely want to practice. But let me know if this is something I can go through with you. I'd be happy to help and go through some extra problems with you in terms of this. So let me throw in a bonus problem here for you real quick. So what if I said find QO? So see if you can kind of pause the video here for a minute and see if you can come up with the answer for QO. So here's what we'd have to do to get from Q to O. So again, I would have to go from QC to CO to get QO. And so remember, that's just the whole concept that we've dealt with in the last section of AB plus BC equals AC, right? You're cutting out the middleman. So I'm going to go QC plus CO is QO. So in terms of what we already have, we know this is not only half of A, but I'm also going in the negative A direction. So I got negative half A plus negative C would get me there. So I'm going to say negative half A minus C, or you could say plus negative C is going to do that. And so you can see if that matches up with what you just came up with. Or if you want me to give you one more if you're still watching, what if we said I wanted to go from A to C? So what if I wanted to find AC? How would I get there? So if you want to give that one a try. So to do that, again, if I wanted to go from A to C, right, I would just have to go from AB to BC to get there. And so we would just call this C minus A would get me from A to C. Or if I wanted to say, what about PO? How would I get from P to O? Right, I would have to go along this line to get from P to O. And so I would say, well, it's negative 2/3 of C. And remember, you'd already have this labeled as 2/3 C, and that would really help. So I'm going to go negative 2/3 C minus A is going to get me there.